All right, so I got OBS up and running. And I'm sending the URL of the live stream. So just give me a moment to get to that. There we go. And then go back to. You can kind of tell that I worked at the Design Hub today from the number of tabs that are open. So that's perfectly normal. All right, YouTube and that. All right, so there you go. So anyone who wants to kind of watch the stream kind of live, you can use this. And then we'll go ahead and get started. All right, so based on the topics that we have gone over, I just want to kind of point out where we are at this point in this class. I mean, you guys should know that already, but we'll go ahead and just make sure. We are done with physical states, truth, numbers, and computers. So where we talk about the Nand Gate, and the significance of that module is we can build logic gates from transistors, okay? Because we use 4 transistors, 2 N channel, 2 P channel, to make a NAND 2 gate. And then it also illustrates how you can use the NAND 2 gate in order to make a regular logical AND, logical OR, and logical NOT gates. So from those, we can say, okay, so we can implement all the Boolean functions that we already know in computer science. So now the question is, what about numbers? We can deal with true, false values, the same way that you have learned in CISP310. But what about numbers? What about calculations? Okay, so that's what we'll be working on today, and also probably kind of for the next 2 weeks or so. Okay, various aspects of how values are represented. Okay, the first thing before we even get into the notes is we need to distinguish what is a value versus what is a number. Is that okay? So do we already know the difference and I don't need to go over that, or do you guys kind of want me to kind of mention it? I'm not 100% on the difference here. Okay, so that's good, okay? So a value is kind of like, if I ask you, what is this as a value, then in your mind, you will think of a word to describe the quantity, the number of fingers, right? So most of us will think of it as 8, right? Because that's the English word to describe the quantity or the value of 8. Is that right? But some of you know other languages as well. So in your mind, that might remind you of another word, okay, in another language that represents exactly the same value. Is that okay? So 8 is a number. Its job is to represent the value. Is that okay? I can give you another analogy, okay? That will be pretty simple, and I think you'll remember this one. I'm a human, okay? But my name is Tak. So the name is more like a number. It is a way for me to tell other people how, who I am and how to differentiate me from other people, okay? But human is kind of like the value. Is that okay? Sort of? Okay, so we are good on that. Because it's really important to separate those two concepts, because we'll be talking about multiple ways to represent the same value. So if that concept, if we cannot differentiate between what is a value versus what a number is, then the discussion will get very confusing. All right? So with that in mind, we are now moving on to the next kind of major module, which is values, numbers, and bases. So in this particular module, we'll learn how to do base conversion and how to interpret a number in some other base, in bases other than base 10, and then figure out what a number, what is the value represented by a particular number. So that's the focus of this particular module. You will need to remember, all the exponent stuff that you have learned from high school, okay, basic algebra, but other than that, not a whole lot, okay? So this should not be a really heavy-duty module, but it's a concept shift, okay? We have to remember a number is just a representation of a value. So we'll go ahead and skip a few things, okay? So we'll skip to this particular section, and we'll basically stare at the base 10 number that we know as 16.375. That's a base 10 number. If I do not have a subscript, if it doesn't start with 0x, if there's no other indication that we are default in this class, it is a base 10 number. So a base 10 number is fairly easy, right? I mean, we all know what is 16.375. So I'm going to spell it out anyway. So we know that it is 10 plus 6 plus 0.3 plus 0.07 plus 0.005. In other words, I'm separating all the digits so that each one appears by itself in a summation. No big deal, right? Okay. And then I look at each digit and I go, well, what is 10? 10 is 1 times 10 to the power of 1. That seems pretty redundant, right? I mean, it's like we know what 10 is. What is 6? 6 is 6.10 to the power of 0, because anything to the power of 0 is 1. Is that okay? That seems awkwardly unnecessary, right? Because, hey, 6 is clean. Why do we want to express 6 as a multiple of a power of 10? Well, that's exactly why. Because what about the 0.3? 0.3 is 3 times 10 to the power of negative 1, because 10 to the power of negative 1 is 0.1, so 3 times 0.1 is 0.3. So I'm not going to say the same thing for the other two digits, but basically we are re-expressing each part or each digit of a base 10 number as a quantity times a power of 10. Now that power of 10 doesn't have to be positive. It can go negative as well. It can also be 0. This example illustrates all of those possibilities. Do we have any questions about how I re-express 16.375 as a very long and unnecessarily complex form? Are we good so far? All right? But that's basically what a number is. Any number that we deal with has multiple digits. The job of each digit is to tell us what is the quantity of this particular power of whatever base we're dealing with. It can be base 10, can be base 2, can be base 7, okay? It can be some really awkward base. Is that okay? So I always start with base 10 because we already understand base 10, okay? But at some point we're going to transition to something else. So to make this abstract, okay? So we are going to use this representation here. So you kind of have to read the notes first in order to understand what is di. So d subscript I is the ith digit, and v is the value. So the way I count digit is the least significant digit that is not a fraction is digit 0. We count from 0. Are we good so far? It's just a naming convention, okay? So in the previous number, 16.375, d0 would be the 6. d1 would be the 1. d subscript negative 1 is going to be the 3. d subscript negative 2 is going to be the 7. d subscript negative 3 is going to be the 5. Is that notation okay? Because I'm going to use the same notation for a while. It is important to understand the notation so that we don't have to go back and figure out, okay, what is d something again? So are we good so far? Yes? Okay. So given that is the case, given how we define d0, d1, d2, d negative 1, and so on, so the value represented by a number is basically a summation of the d something, depending on its position, times 10 to the power of that position. And if you just do a summation, that's the value that is being represented by that number. Are we doing okay so far with this concept? So what I'm doing here is I'm abstracting. I give you a concrete example, and then I abstract it using variables and unknowns and symbols. Is everybody comfortable with the sigma notation? Because I'm going to use the sigma notation quite a bit in this class. If someone is not comfortable with the sigma notation, I can explain it, and I should probably explain it now because it's going to be reused a whole bunch of times throughout the semester. So are we good with the sigma notation? Go through it really quick. Okay, very good. So the sigma notation, okay, I think it is probably better off if I use the tablet for this because I can draw that. So we'll go ahead and go to accessories and then journal. This basically just gives me a digital whiteboard. So this way, whatever I write is also captured in the video. Okay, that. Any questions? Any questions I can answer? Nope. Okay. So we're going to start with a sigma notation. And I'm just going to say, I is the index variable. It goes from some b value to some e value. And then whatever is in between, whatever each term is, I just call it a function f of I. Is everybody comfortable with the function notation? F of I is really just a function with a parameter I, and it returns some kind of value. Are we good with this? Okay. All right. So the next part, I don't need to use my tablet, and I am going to use a notepad because I'm going to give you the C code that does exactly the same thing. Are we good so far? So here we go. Okay, so I'm testing how well you know C at this point. Okay. So let's just say that we are dealing with integers for now. Okay, so the type of the function is always returning an integer. Or if you guys want to, we can say it's returning a double. Okay, so we can say double. Okay, so the summation is going to return a double as well because it is a summation of double values. Okay, so we say this is our sigma notation. So each one of the things on this side, b, e, and f, are parameters. Okay, so we got double b, double e. Okay, those are easy because b and e are really just individual values. But what about the function? Can we pass a function to another function as a parameter in C or C++? The answer is yes. Okay, very good. It is called, well, depending on how object-oriented you want to get, I'm not really a big fan of object-oriented programming, so I'm just going to use a pointer to a function in this case. So the way you specify a pointer to a function is kind of like this. So you still have to specify the return type, and then where you would normally put the name of a function, you use parentheses to enclose star or the asterisk, and then p func, okay, pointer to a function. And then you specify the parameter type, which is a single double. So this is how we specify all the parameters that we need in order to calculate the sigma of a function. Now it's passed in as p func, and the start value is b, the end value is e, and now we just have to figure out, okay, but how does it work? Are we okay so far with this? Okay. So we can now make an assumption that b is always less than e, okay? Because if you want to generalize, we can kind of check and flip things around a little bit, but let's just say that we make the assumption that b is always less than or equal to e. Is that okay? All right. So now we just say, we can do it with a while loop. So we'll start with a sum first, okay? So sum is just a local variable. It is initialized to 0. And then what we do is we can either use a while loop or use a for loop. There's really not a whole lot of stuff to gain using a for loop, so I'm going to use a while loop. So I'll say while b is less than or equal to e, do the following. So what we do in the loop, Now you will find out that trying to copy my programs as I type is not a good idea, because I do this a lot. Okay, I just open and close the curly brace and then I insert stuff in between. So it's best not to do it. It's a better idea to ask me to check to see if we are streaming and whether the audio is also on in the stream. So we'll go ahead and double check because I just said it, right? And oh, I just passed it right here. And you can't see the bottom of the screen, but it is green and the audio bar is fluctuating. So we are good, okay? So just check with this, check with me, once in a while, to make sure that I'm not forgetting to turn on the recorder, or I'm forgetting to turn on the mic. Okay, so we're good right now. So there's no need to copy everything. You might want to kind of jot down the concepts or ideas that you feel is important. Okay, anything that I'm speaking, anything that is on the projector is already recorded, but I cannot record your thoughts. It'd be super creepy if I could, right? All right, so as long as P is less than or equal to E, okay, I is basically, B is taking the role of I, kind of, it's doubling as for that particular purpose. So we'll just say the sum plus equal to P func applied, and then we use B as the parameter. So this is how you use a pointer to a function, is you kind of use it in the place of a name of a function, and it will automatically figure out that this is a pointer to a function and call the function that is pointed to by P func, and using B in this case as the parameter. So once we do this, we add 1 to B. Did I make a mistake with the syntax? I'm fairly sure this is the way to use a pointer to a function, but I could be wrong. I think the asterisk is optional. It is not necessary. Okay, and then we add 1 to B because we want to move on to the next value. Okay, and when it is all done, we return sum, and this is it. So on the left-hand side, you have the mathematical notation, and then on the right-hand side, you have the C definition of pretty much the same thing. Are we good so far with this? Yes? Okay. So whenever I try to explain something, I will try my best to relate it to something that you have already understood, or I think you should have understood already. If my assumption is wrong, you can raise your hand and let me know. Are we still doing okay? All right. All right. So now that this part is okay, that's how I find my pointer, by the way. I just pressed the key accidentally, but if you want to see again, this is how it works. And I can move my pointer around as that is happening. That's kind of cool. All righty. So if you have a number, okay, I don't know ahead of time how many digits there are, so I'm just going like, okay, let's just say that it has a lot of digits to the right-hand side of the decimal point and a lot of digits to the left-hand side of the decimal point. So that's why I is going from quote-unquote negative infinity to positive infinity, just so that, because a number can have any number of digits that you want, okay? If you just say that, but your number doesn't have that many digits. 16.375 only has 5 digits. Well, just imagine a whole bunch of zeros to the right-hand side of the 5 and a whole bunch of zeros to the left-hand of the 1. Okay? So you can basically make it as long as you want without changing what it is representing, just by padding zeros to both ends of a number. Does that make sense? Okay? All right. But you can see that, but not everything is parameterized. There's a literal number here. There's a literal value of 10 in this case, because that's base 10, okay? Because the previous example is a number in base 10. That's why we use powers of 10 in this case. So what if we switch to some arbitrary number, as a base? Okay, what do you think? Change the 10 to whatever base you're using. So in this case, I'm using b as a variable to represent the base. Okay? So now the equation is even more generalized, because now it's saying you can use any base you want, as long as I still have all the digits, I can figure out what value the number is representing. Are we doing okay so far? Okay, good, good. All right. Section 5 talks about, how do we convert a value to a number in a particular base. Okay? So you're given a value, okay? For instance, you're given this value that we normally know as 9, right? But I tell you, I want to represent the value 9 in base 4, okay? So now the question is, how do you know what is the base 4 representation of the value that we know as 9? Okay? Now, what if I tell you that you already know how to do this? It's just that you never associate a skill that you already have to base conversion. Would you be curious? Yep. You can, yeah, yep. Yep, because the 2, yep, exactly. But the concept of base conversion, you have already understood, okay? Unless you don't feel comfortable, if I just say that, okay, I need to make change for $26.75, okay? If you say, I'm not really comfortable with, making that change using the least number of bills and coins, let's say if you're working for McDonald's, then you might have a problem with that concept, okay? I'm assuming everybody in this class feels comfortable, if you give me the amount of change, I can do it using the least number of bills and coins, or whatever is available, okay? Is that a safe assumption? Okay? Because, okay, so let me show you one thing that will illustrate, this point here. So I'm going to go back to Notepad, and this time I'm going to look at all the different coins and bills, all the commonly used ones in US currency, okay? And we're going to start with the smallest one, okay? So what is the smallest denomination in the currency? A penny, okay? A penny is known as 0.01 of a dollar, okay? So we're going to use a dollar as the unit, okay? What is the next one up? A nickel, and the next one is a dime, and the next one is a quarter. And we're going to skip a half dollar because they're not really common, okay? So what is the next one? A dollar bill, okay? So a dollar bill. Next one is, there are $2 bills, but they are not very common. So we skip to the next one, which is 5, and then 10, 20, 50, and we can stop at 100 because I never really have that much money. So we can stop there. But what we're interested in is, I'm assuming all of you feel comfortable dealing with all of these coins and bills, and you can figure out how much money you have based on the coins and the bills. And if I tell you, okay, I need exact change for $10.65, you know how to do it. Yes? Okay. But that is far more complex compared to base conversion. Why? Because if you look at the denominations and look at the multiplier to get to the next one, let's see if there's any regularity to this whole thing. Okay? It's a 5, right? Going from 1 penny to 1 nickel is a multiplication of 5. This is a multiplication of 2. This one is odd, 2.5. How do we get that? And then we have 4, right? And then we get back to 5. And you would think, oh, okay, this is the beginning of the next cycle. No. 5, 2, and then you would think, okay, 2.5 is the next one. No, we got another 2, and then we get a 2.5, and then we get another 2. There's no regularity. We know that the multiplier kind of is between 2, 2.5, 4, and 5. Okay? But that's about the only thing we know. And yet, you can deal with it, right? So what if I were to propose a new currency system, which will piss off a lot of people, but to computer science people, they'll go like, that makes sense. We start with the dollar bill. And then we have $2 bills. Then we have $4 bills. Then we have $8 bills. Then we have $16 bills. Then we have $32 bills. Okay? They're all powers of 2. Okay? And then on the flip side, we go like, but sometimes, I want to buy something that's less than $1. Okay, fine, have a $0.50. But I want something that is even less expensive than that. Have $0.25. But what if something that's even less? Have $0.125. Okay? If you can deal with the current currency system, the new one is easy because everything is just twice of the previous one. Yes? But that gives you the idea of base conversion, because if you can deal with something this complicated, this is easy. Okay? So kind of keep that in mind, when we talk about the base conversion. Okay? All right. So getting back to the notes. So what we want to do is we want to figure out what is a particular digit. So there are many ways to do base conversion, and I can show you by hand, how to do it, a very basic base conversion. So let's just say that we start with a bigger number. 9 is kind of too easy, so we'll start with something that's even bigger. And we want to convert it into base 4, okay? So the way we do it is, let's say we start with 121 in base 10. So 121 in base 10 is the value that I want to express, but this time in base 4 as a number. So what we do is we divide it by 4. Okay? And we look at this and go like, yeah, we know what it is. It is 30 with a remainder of 1. Is that okay? Then we look at 30 and we say, let's divide that by 4. So 30 divided by 4 is 7 with a remainder of 2. 7 divided by 4 is 1 with a remainder of 3. And we can stop here. But for those of you who say, I don't want to stop, we can keep going. 1 divided by 4 is 0 with a remainder of 1. And if you say, I don't want to stop because this is so much fun, we can keep dividing 0 by 4, which is 0 with a remainder of 0. So you can see how any further division by 4 is not going to give you anything that's interesting. It will just give you a whole bunch of zeros, right? You also can see that, all of these digits, okay, if you look at all the remainders and the last, we call this quotient, okay, they're all between 0 and 3. Because as a base 4 number, the digits that you can play with go from 0 to 3. Just like in base 10, the digits only go from 0 to 9. 10 takes up 2 digits. Is that making any sense? Okay. So how do we read this number? Well, the way you read this number is the first remainder is digit 0. And this is digit 1, digit 2, digit 3, digit 4, digit 5, and all of the other digits, digits 6, 7, and so on, they're all going to be zeros. Okay? So the way we write this is, okay, ignoring all the leading zeros. So we can say 121, and I emphasize this is in base 10, is 1, 3, 2, 1 in base 4. So this is how we do base conversion. It's really just a whole bunch of divisions, and then with each division by the base, we keep track of the remainder. Yes?
Isn't it 1, 3, 3?
Huh? It's 1, 3, 2, 1. Now, okay, so here's the question. Okay, did Tech make a mistake? That's a very legitimate reason. Okay, for those of you who have taken classes from me, I make mistakes all day long. And then I say, well, but I'm really just testing whether you guys were paying attention or not. Okay? So how do you check whether this makes sense or not? How do you know whether 1321 is really representing the value of 121 in base 10? How do you check it? You look at, so you have to reuse something that you have just learned. Okay? What have you just learned? If I give you a number and I tell you what base it's in, you already know how to figure out its value, right? So this is D0, this is D1, this is D2, and this is D3. The base is 4. Figure out the sigma. Okay? Is that okay? Are we relating back to what we have just learned moments ago? Yes? So let's go ahead and carry out the math, okay? See if it makes sense. This one here is telling us how many 4 to the power of zeros do we have, and that's why it's called digit 0. This 2 here is telling us how many 4 to the power of 1s we have. That's why it's called D1 or digit 1. Digit 2 and digit 3. So we can just go ahead and carry out the multiplication. So over here, I just, okay, I'll just write down these are powers of 4. Okay, 1, 4, 16, and 64, right? Those are all powers of 4. Are we good so far? So we multiply each digit by the power of 4 that is corresponding to it, and then we just sum up everything. So what do we get? We got 164. We have 3 of 16 that will give us a 48. We have 2 of 4, which will give us an 8. And then we have 1 of 1, which gives us a 1. So now the question is, does that add up to 121? I don't know. I mean, you guys can double check. Okay, so we'll just do a quick math here. 64 plus 48 is 112, okay? 112 plus 8 is 120. 120 plus 1 is 121. So according to my mental math, it does add up to 121. So are we good so far? Yep. Okay. All right. So let's go ahead and move on. If you do have questions, you kind of want to raise your hand and ask the questions, because I don't slow down or stop unless you guys have questions. All right? Okay. So what if you're only interested in one particular digit? Okay, so all of this is explaining the process in order to derive this little equation here. So this equation is it only gives you one digit of the number based, using b as a base, and it will only give you digit I. Okay, whatever I is, it will only give you that digit I. But that I can be 0, can be 1, 2, 3, 4, but it can also go negative. So you can actually figure out I shouldn't say decimal point or decimal values because it's not deci anymore, but you can figure out the fractional part of a number using a negative number or negative integer in place of I. Are we doing okay so far? You look at this and you question it, right? You have to question everything when I'm teaching a class. Okay, I don't know about your other classes, but I encourage people to question everything because I do make mistakes, okay? So you want to say, well, I'm not really so sure about this, okay? How do we test it? How do we do a quick sanity test and go like, oh, okay, I see it does work out, okay? How do we test it? We just use the base 4 number that we have just introduced as an example, right? So let's say we want to work out D2, okay, which is a 3 according to the earlier conversion, okay? So we want to figure out D2. So I is 2. So V is 121, and B is 4, because that's the base that we're dealing with. 4 to the power of 2 is 16. 121 divided by 16 is... I know it's at least 6. I think it's a 7, right? I mean, you guys have calculators. I know you guys have fancy TI-84 CE calculators. Yes?
Sorry, V was 3?
V is 121. I'm using the same example as
I is 3.
I is 2, sorry. I is 2 because we count from 0. Okay, so let me just write it down here so we can see it. Okay, so we want to use I is 2, B, which is our base, is 4, V is 121, right? And then the equation goes like this, v divided by b to the power of I. Take the floor of that and then mod it with whatever b the base we're dealing with, okay? So this particular symbol is the floor symbol, okay? The floor symbol means, whatever you're taking the floor of, we want the largest integer that is less than or equal to that thing. I can even write it down a little bit here. So the floor of x is the largest integer that is less than or equal to x.
So it's 7, because 7 multiplied by 16 is 112.
Yes, so 7 point something technically is 121 divided by 16. Then you take the floor, 7 point something becomes 7, right? And then b is 4, 7 mod 4 is, oh, magically it matches our digit 2. So that's a quick way to do a sanity check, okay? Based on things, examples that we have already gone through, you just reapply what you have learned and go like, but is this consistent with all that, okay? Now I could have introduced something that is completely wrong, but in itself consistent. So we could never really spot any problems. Okay, but that takes a lot of work, and that's one thing I do not do. It's a lot of work. All right, so are we good so far with base conversion? Okay, all right. Cool. Now the other thing you can also do with this one is just play with base 10. It sounds really stupid, but it's one way to really look at this and see how it works. Okay? In other words, you use v, as one of the examples, like 16.375. Okay? You say b is base 10. So you're converting from base 10 to base 10. But you should still be able to get the digit right? And then you just say, well, this time we want to try out some negative integers for I. So let's try -3 for I. Go through the calculation. Are you getting back the 5 in 16.375? Try it out, okay? And see how it works. So I'm not going to go through that. It is a suggested activity that you can do on your own. And you will hear me saying that a lot, okay? I highly encourage you guys to do blah, 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 blah. Usually that means I think it is going to help, okay? You are free to disagree with that and say, I don't think so, and don't do it. Because guess what? At the end of the semester, it's not my grade. My grade was done decades ago. So you get to decide for yourself, okay? How you want to study and do the exercises for this class. So now we finally move on to binary numbers. But there's really not much to say. Because with a binary number, which is base 2, that simply means that b, which is representing the base, is 2. Done, discussion over. It really is over, okay? So what is the rest of this stuff here? The rest of this stuff is really just explaining, okay, how that works. So, this is just an example. For those of you who want to go through an example, this is here's a concrete example. So with a base 2 number, I use a subscript 2, or if I use Notepad, I would put the 2 in parentheses because it's hard to do a subscript when you're just using a text editor. But I would use a 2 here, or in parentheses 2, to emphasize that this number is in base 2. So do not tell me this is 1101, because it is not. Okay? Are we good so far? So this is 1101 in base 2. So what we want to do is to say, okay, but what value is it representing? This 1, which is digit 0, is telling us how many 2 to the power of zeros do we have. We got one of those. This 0 is telling us how many 2 to the power of 1 do we have, because that's digit 1. We got none of those. This 1 is telling us how many 2 to the power of 2s do we have. We got one of those. This 1 is telling us how many 2 to the power of 3s do we have, and we got one of those. The rest are all zeros. So what we end up with is 1/8, which is 2 to the power of 3, 1/4, which is 2 to the power of 2, and 1/1, which is 2 to the power of 0. You add up those, 8 plus 4 plus 1 is 13, what we know as 13 in base 10. So is that okay? How 1101 in base 2 is representing the value that we know as 13. Yep?
Just for clarification, so basically every base we would refer to it the same way, like the last one we did for base 4 would be 1, 3, 2, 1, base 4.
Mm-hmm.
So base 10 is the only one where you would actually name it the number.
Say that one more time, the last sentence.
Base 10 would be the only one where you'd actually call it that number.
Correct, yes. Because in base 10, we already have specific terms to refer to commonly used values like 32, okay? Because since elementary school, we have been poisoned by base 10. So in order to feel happy and comfortable, we kind of have to continue the use of base 10. You guys will see why I say we have been poisoned by base 10, because it really is bad for us. All right. Are we good so far with base 2, which is just saying, oh, instead of 4, we have 2. Is that okay? Does anyone have a problem if I say, well, let's go ahead and use base 7, which is kind of odd, right? I mean, 7 is not 2, it's not 10, it's not any power of 2, it's a prime number. Can we use base 7 to represent values? Exactly. The answer is why not? Okay, so who would use base 7? I mean, we use base 10 because of 10 fingers, right? Yes?
I used to use base 7 when I wanted to annoy my math teachers in elementary school. I would number my homeworks in base 7.
Aha, okay. Well, you got some buddies under the ocean, under the sea, okay? Because I think, octopus will also use base 7. And then you guys would go like, tag, I think octo means 8, okay? Yes, but if an octopus wants to leave one tentacle to hold the beer, then it only has 7 left to do the counting. And don't ask me how octopi drink beer under the water, okay? But they're smart, okay? One thing we know is octopi are very smart animals. They don't live very long and they are tasty, but they're actually pretty smart. You can watch all kinds of videos on YouTube at your own time, okay? Not during class, but there are a lot of videos showing how octopi are actually very smart. And not only that, they are super escape artists. If the beak fits, they can get through. And they can actually walk on land for a little bit too. They can hold their breath. Okay, so now that I have talked so much, I have to tell you, there has been a mystery in an aquarium. I think some of you have heard of that, right? So they have octopi on one side of the aquarium, a walkway for people, okay? On the other side, they got some crabs or, some other animals, okay? And they will occasionally find or constantly finding, the crabs are missing, okay? How can that happen, right? So they found that, the octopus would kind of sneak out of his tank, cross the walkway, get into the tank that has all the crabs, eat the crab, and then walk back to his own tank and pretend, don't look at me. It was quite interesting. I have a friend who lost a few octopi because he did not close up the tank, so he left a gap so the octopi would actually get out, because remember, if the beak fits, it can get out. So the octopi would get out, explore, and then forgot how to get back. Yeah. So Yep. So that's the problem of not having a GPS-enabled smartphone, which I have no doubt octopi can learn how to use if they get enough exposure. Okay, so section 7, how are values represented in a computer, in a digital binary computer? I think the question contains the answer. What is the answer? In base 2, yep. So a computer basically represents everything in base 2, okay. What about those programs that you have written in C and C++ where you specify constants in base 10, or you use cin so they can read a number in base 10, right? So to you, it would seem that the computer actually works with base 10 numbers. Well, it works with base 10 representation, okay? So the computer actually has to, your programs, okay, using cin, would actually have to go through quite a bit of processing in order to convert what you type in as base 10 into its native internal representation, which is in base 2. Okay, so do not be confused by the fact that you can enter numbers in base 10 and you can specify base 10 constants in your program. The computer actually has to work extra hard to understand the base 10 numbers and convert those into the internal representation. Okay, all right, so section 8 talks about an exercise. Okay, you can look at this as an ungraded assignment to do base conversion. So it's up to you. Okay, if you want to apply what you have just learned, okay, you can write a simple program. You let the user to type in the base that you want the program to work with, and then the number, and then the program will figure out the base 10 representation of that value. Is that okay? So the input is the base, the number in that base, and then the output is the number, or a number representing the same value but in base 10. So that a normal person can read and go like, oh, okay, I can see the base 10 representation is this, okay? Then you write a second program to do the reverse, okay? You type in a value in base 10 as a base 10 number, and then you specify what base you want to convert that value into, and then the output of the program would be a number in the base that you have just specified. So you can write those two programs, okay, if you want to, because in the process of writing those programs, I think you will get a better understanding of the concept, and it gives you some extra time and extra pathway in your mind to make all the connections. Okay? If you disagree and say, no, I think this is not going to help me, okay, don't do it. This is ungraded. It doesn't count for any points. It's just a suggested activity that I think may help. Is that okay? All right. That's a pretty easy slide, easy module. Are there any questions? Yep.
Then the formula, like algorithm for converting like a single digit of a number, you can start with any base and convert it into any other base with that. You don't have to start with base 10.
That is true. You can start with any base. So now you have to specify the from base, the to base, and the number in the from base. So you can combine those two programs. Yes, absolutely. Or you can write two programs and then pipe. Well, actually, you need to cat and then pipe. Yep. But there are many ways to do it. The point is, try to write a program to exercise, and just use the concept that you have learned. All right. Are we comfortable with base 2 numbers? Yes. Okay. Well, okay, I got one extra thing to do because I do want to kind of go back to the example, which is 16.375 in base 10. I want to know what is this same value, or what is the value represented in base 2? What do you think? Now remember, if you're converting to base 2, think in powers of 2. Okay? So you basically have to ask, okay, let's enumerate all the powers of 2 that seem to be useful in this case. Okay? So we start with a 1, then we have 2, we have 4, we have 8, we have 16, we got 32, And on the other side, we got half, quarter, eighth, and if you want 16, then so on, okay? Now, the nice thing about base 2 is you either have or have not a particular base. You don't have to worry about, oh, I think we got 2 of those. No, it's either 1 or 0. It's either there or not, okay? Which makes it super easy to deal with. So the trick is to start with the high power first, okay? Start with 32 in this case, okay? So you ask, do we have a 32 in 16.375? The answer is no. Put a 0 here. Then you move on to 16, okay? That's kind of obvious. 16 has 116, right? So you say, nope, there's 116 here. But once you have taken the 16 out, you only got 0.375 left, right? So 0.375 doesn't have an 8, doesn't have a 4, doesn't have a 2, doesn't have a 1. So all of those are zeros. Are we good? Then you move on to a half. You go like 0.375 is less than 1/2. We don't have a half. Then you look at a quarter and go like, yep, we got one of those because a quarter is 0.25, right? So 0.375 has 1.25 in it. Put a 1 here. What is left? 0.125. Then you look at 1/8, which is the next one up, and you go like, oh, an eighth is exactly 0.125. Put a 1 here. Is that okay? So the answer is none of those, one of those, none, 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 none. And you put a point here. That is the whole purpose of the quote-unquote decimal point. It's not decimal anymore because we're not using base 10. But the whole idea of the point is to tell you where digit 0 is, okay? Because it is always between digit 0 and digit -1. That's what the point is trying to represent. Unless you're European, then you use a comma. Yes? Okay. Okay, so we got none of half, 1 of quarter, 1 of eighth, and then none of those others either. There you go. So the base 2 representation of 16.375 is 10000.011 in base 2. Yep.
Does the computer need another bit to store the decimal?
No, the computer has a different way of maintaining where the point is. So when we get to double representation of floating point numbers, we'll talk about that. Okay, so that's a very good question. You're thinking ahead, but we are going to stick with integers for a while, and then we'll move on to floating point numbers. All right. So are we good so far? Are all the examples okay? All right, cool. So now we get back to the notes because now we are ready to move on to the next thing. And the time is 6:25. We got plenty of time. So now we are moving on to binary number addition. So this is the next module. So tonight, our lab is going to do base conversion for sure, okay? I'm going to save multi-bit stuff maybe for the next lab. So tonight, we'll just do the base conversion lab. All right, so we'll go ahead and start with this one. I'm moving into a new window because I can't keep track of all those tabs. Okay, so when we talk about adding, the first thing we do is we go back to base 10 because I suspect that some of you have forgotten how to do addition in base 10. Okay? Because I want to ask you, you're looking at an example. I'm going to ask you something different from the example. What is 6 plus 8 in base 10? There are several ways to answer this question. Okay, most people will say 14, okay, which is correct, but it is also known as 4 with a carry of 1. Does that make sense to you? 8 plus 6 or 6 plus 8, because it's commutative, is 4 with a carry of 1. No? Okay, so the reason why I said that is because this is how we set up for multi-digit addition. Okay, single-digit addition is useful, but it's You can only go so far, right? Because with a single digit in base 10, the best you can do is 9 plus 9, which is 18. Okay? How much is a textbook? Unless you're talking about this class, because that would be a 0. But in most cases, a book is more than $18 already. So you want to be able to add and subtract more than 18, okay? So you need multi-digit addition. So for this, I'm going to switch to Zerno again. So what we'll do is we're going to carry out a multi-digit base 10 addition, but in a very strange format, okay? So I'll show you why I say it's kind of strange. So we have 8, 1, 6 plus, I don't know, 1, 2, and 8 here. Okay, so there we go. So this is all in base 10. We're talking about 816 plus 128, okay? You guys know how to do this, okay? But I'm going to do it in a very special way. So we're going to call this row X. We'll call this row Y, okay? And this is consistent with further discussions. So I'm just introducing some of the representations or symbols that we'll be reusing over time. I'm going to call this row, gosh, I cannot remember what it was, Q, that's it. Okay, so this row is named Q. This one is called K, and then this one is S, okay? It's just, how I name those particular rows. All right. So I'm going to do it this way. There's no carry to digit 0 because it's already the least significant digit in this particular addition. Is that okay? So the K row is representing carry. That's all, that's its only job, is to say, do we have a carry into this particular column? And digit 0 has no carry into it because it's already the least significant digit. Is that okay? Okay? All right. So now we actually do the addition. 6 plus 8 is 4 with a carry. This is where you put the 4, and then the carry goes to the next column. Is that okay? Now you do this in a very kind of different notation, okay? You just don't use an entire row for K. You just kind of put a little 1, next to the line. But I'm going to use a very explicit representation because later on we'll try to figure out, how do we do all this using logic gates in base 2? And it is important to spell everything out, okay? And then we have a 4 plus 0, which is a regular 4, okay? No big deal. Then we have 1 plus 2, which is a 3. And then we have 3 plus 1, which is a 4. Neither addition, okay? 1 plus 2 does not give us a carry of 1. 3 plus 1 does not give us a carry of 1. So we put a 0 here because none of the 2 additions of the middle column is giving me a carry of 1. So we put a 0 here. And then we say, what is 8 plus 1? It is 9. What is 9 plus 0? It is 9 also. So now we have 944 as, or 944 as the sum of those 2 particular numbers. Is that okay? Yes, go ahead.
We just keep going with carryover lines.
The carryover
Like,
lines.
say, we had in the second digit place, the tens place.
Mm-hmm.
If that was, that equaled like 12,
Mm-hmm.
would you just add an extra carryover line?
Nope. No, that so-called 12 would have the 1 going here.
I mean, okay, so if the Q and the K
Mm-hmm.
added up to 12, you just put the 1 in the K?
Mm-hmm.
Okay.
The K row of the next column.
Okay.
Yep. Is that okay? All right. I'm hoping this is not presenting any challenge in this class. Okay, so we are all good? All right, cool. So the next thing we do, and you will see that I do this often, is to do an abstraction of all of this, okay? So what we do is we are going to say R of xy is, I'm going to call this the partial sum. Doesn't matter how you want to call it. Okay, so I'll just call this the partial sum. And then C of xy is the carry. Ooh, what happened there? Of x plus y of x plus y. Okay, so let me clarify what I mean by that by using several concrete examples. So R of 6, 8, keep doing the same thing. I think it's picking up a click from something. That's a 4. Because that's a 4 in 14 when you add 6 to 8. And then the carry of adding 6 and 8 is going to be a 1. Is that okay? So let's go do another example. Okay, what is the R of 1, 3? The partial sum of 1 plus 3 is 4. Okay. And then the carry of 1 plus 3 is 0. Very good. So I'm hoping you guys already are starting to understand what I mean by partial sum, or what the R function is doing. It's really just taking that least significant digit of a sum and ignoring the other digit. Is that okay? And then the carry is basically saying if a single digit cannot represent the sum, okay, then we have a carry of 1, because we need to rely on the next digit in order to represent the full quantity of the addition. Is that okay? So how long did it take you to memorize the R and the C for base 10? In other words, your elementary school teacher will quiz you, right? Will say, oh, what is 2 plus 9? Okay, and you have to say, oh, it's 11, or 1 with a carry of 1. So how long did it take you to memorize that? A little bit of time, okay? I think to master it, it would take maybe 2 to 3 weeks, okay? Because there's a lot to remember. Even though addition is commutative, there's still a lot of entries in it. Subtraction is even worse, because subtraction is not commutative, okay? We'll move on to subtraction at some point. So now we want to look at this and go like, okay, so what does it look like in base 2? Okay, so we want to look at base 2. So if you look at base 2, okay, if I say 1 in base 2 plus 0 in base 2 is 1 in base 2, does that make sense to you? What does 1 in base 2 represent? What is the quantity that it is representing? It's a trick question. Just 1, exactly. What do you think 0 in base 2 is representing? 0, okay, so 1 plus 0 is 1 is universally true regardless of the base. Is that okay? All right. And it has no carry, okay, carry of 0, right? Because the sum between 1 and 0, which is 1, can be represented by 1 digit in base 2. Because 1 digit in base 2 can represent 0 or 1, but since it's just 1, hey, we're good. We don't need the next column. Okay? Is that okay? Because addition is commutative, so that kind of comes automatically. The next one is, okay, let's do this one first. Okay, super hard. Yes? Okay. And that's not oxygen. Because your chemistry professor will go like, no, I don't think so. All right. So the last one is the only one that's tricky. 1 in base 2, and that's not iodine. 1 in base 2 plus 1 in base 2 is what we know as 2 in base 10. But because in base 2, you can only use the digits 0 or 1, you go like, oh, darn, I don't have a single digit that can represent this quantity because it's too much. So it has a result of 0 with a carry of 1. Okay, so it has a partial sum, which is what we know as R, and a carry of 1. So when you look at this table, are we okay with this? Because we don't want to move on unless we are okay with this little table here. The only tricky one is 1 plus 1. That's really the only tricky one. Is, oh, okay, we got 1 and we have 1. But in base 2, you don't have a digit to represent the quantity of 2. So now you have to say, oh, it's 1, 0. Because remember, in 1, 0 as a base 2 number, that 1 is representing the quantity of 2 to the power of 1, which is 2. So 1 plus 1 in base 2 is 1, 0. Actually makes sense. But are we okay with this table? Separating the partial sum that I call R from the carry, which is C, as a function. Yes? Okay, all right. So next, I'm going to clean that up a little bit. Okay, so I'm going to make a new page. New page after. Okay, there we go. So I'm going to clean it up. Okay, we say what is X, what is Y, what is R, and what is C. Okay, and this time I'm going to make it nice so that we have, it's a much more systematic way to do this. Okay, so we have 0, 0, 0, 1, 1, 0, 1, 0, and then 1, 1. So I'm just going to copy stuff from before. Okay, the partial sum of 0 plus 0 is 0, and that addition does not end up with a carry. The partial sum of 0 plus 1 is 1, and does not end up with a carry. 1 plus 0 has a partial sum of 1, does not end up with a carry, and then 1 plus 1 has a partial sum of 0, but it does have a carry. Okay, I'm just recapturing what we wrote a little bit earlier, but in a truth table way. Okay, so you look at this truth table, and we say X and Y are the given. Okay, I'll give you the X, I'll give you the Y, and I'm going to ask you, what is the R value, or what is the C value? Okay, so we want to express R and C as functions of X and Y. Is that okay? So when you look at, we'll start with C. Okay, when you look at this column versus these two columns, and you just kind of concatenate those two, does that truth table remind you of a Boolean operator that you should be quite familiar with at this point? Just logical AND, right? Because 0 and 0, or false and false, is false. False and true is false. True and false is false. The only time you have a true is true and true. Is that okay? Cool. And then this column does not correspond to something that you are already familiar with, because in C and C++, we don't have an exclusive OR operator. Okay? So let's rewrite it a little bit. Okay? So carry of X, Y in base 2 is really just X and Y. Now remember, in this class, I use the shorthand in electrical engineering, where multiplication is overloaded as conjunction, and then addition is overloaded as disjunction. Okay? So the carry between X and Y is just X and Y. Okay? What about the result, the partial sum? The partial sum of X and Y, if you want to use exclusive OR, that's fine. Okay? You can just say that it is X exclusive OR with Y. So exclusive OR is very commonly written as a plus with a circle around it. Okay? But since we don't have exclusive OR as an operator in C and C++, let's try to figure out how to express this in C and C++. So in C and C++, it's going to be not X and Y, or X and not Y. Let's see if it makes sense, right? So we want to, I'll leave this up to you, okay? Apply this equation or this expression to every single row of the truth table and see if the result is the same as the R column. Okay, that's kind of what I want you to do. I can do one row for you. Okay, let's pick this row here. X is 0, Y is 1. So X is 0, not X is true. Y is a 1, so we got true and true. So this part is true already. Then we have this part here, X is false, right? So we don't need to look at the rest, because if one component of a conjunction is false, the whole thing is false. So now we end up with true or false, which is true. So that does match this little value over here. So you just have to do this for the other 3 rows, then you'll be convinced that this expression does work out. Okay? Now, if you're confused about the negation symbol and go like, what is it negating? It's always just negating whatever is to its right-hand side. So if I want to add additional parentheses, that would be it. Are we okay so far? Good? I look at this and go like, this is great, because we have just converted an arithmetic operation of addition into what? Conjunction, logical not, logical and, logical or. What are those things? Logical operators. Wait, I think last time we talked about logical operators and how all of those, logical and, logical or, and logical not, can all be implemented by Nand gates, okay? Maybe not one, a bunch of Nand gates can do all of those, right? But wait, before that, we talked about how we can use 2 p transistors and 2 n transistors to make one Nand gate. Yes? So that means all of this, okay, can be done by a bunch of Nand gates, which also means they can all be done in transistors. If you are thinking, because I know some of you are not good at expressing, if you're thinking, wow, this is great, because we have just connected arithmetic operations with Boolean operations, which can then be implemented using physical devices known as transistors, you are absolutely right. Okay? Because I know some of you guys, okay? You have a party going on in your head. People just cannot see it from the outside. I'm kind of the same way. There's a huge party going on right now.
This would be a huge discovery 60 years ago.
Huh?
This would be a huge discovery 60 years ago.
Say the moment.
I said it would be a huge discovery 60 years ago.
6 years ago?
Yeah.
Why?
Because that's time they know that they used transport 8 years ago.
8 years ago?
80.
80, okay. Well, but you can do it with relays too. You can do it with electromechanical devices, because there are equivalences to the p and n transistors in the form of relays. So if you want to go to, no, it's not called Grand Auto anymore. That kind of dates me. O'Reilly, right? You know, the auto supply store. Okay, you can go there and buy a whole bunch of relays. Okay, and then you can implement Nand gate using 4 relays. This is just a whole bunch of Nand gates, okay? So you can say, I can implement all of these things using a whole bunch of relays. Now you need a lot of juice to do it, because relays are very power hungry, but you can do it, okay? But wait, hold on a second here. This is only doing single digit addition. Do we know how to do multi-digit addition, knowing that now we know how to figure out the partial sum and the carry? So that's the next question, right? Okay, so now we want to look at addition, but in a slightly different way. I'm going to give you digits, okay? This is digit A, this is digit B, this is digit C. I need to be mindful of time. We got 5 minutes. We got enough time for this. And then we have, you know what? I just lied. We call this x2, x1, x0, y2, y1, y0. In other words, these are just individual digits of the xy that we dealt with earlier. But I took this to a level of abstraction. I'm not giving you actual digits anymore. I'm replacing each digit with a notation. Is that good? All right. So you remember this one is called Q, right? So this is Q0, Q1, this is Q2. This one is K0, K1, and this is K2. And then this is sum, S0, S1, and this is S2. Okay, cool, right? I mean, we have just replaced all of the digits with symbols. So now we want to figure out the relationships between the symbols, okay? So if I say, I want to figure out what is Q of I. What is Q of I? using the R or the C or combinations of those two. What is Q of I? It's the partial sum of xi plus yi, which we know of. Which function does that? The R function. Very good. Okay, so R of xi yi. Okay, that seems okay. I think the sum column is kind of the same thing, except it is the partial sum of q and k. Okay, very good. So it's qi, ki. Cool. Okay, the k row is kind of the tricky one. Okay, so k0 is usually assumed 0. Okay, I say usually because later on we'll figure out why sometimes it's not. Okay, but what about k of I plus 1? Okay, in other words, if I want to look at k1, who can contribute to k of 1? There are two sources, right? Because x0 plus y0 can have a carry, but q0 plus k0 can also have a carry. So it's going to be the carry of xi, yi plus, okay, now this is not or, this is the actual plus, okay, plus the carry of qi, ki. Yes? So knowing the R and the C function and knowing how multi-digit addition is structured, we now can figure out, okay, give me an n-bit number, and I can add it to another n-bit number and figure out the sum using just the functions that we have defined, C and R, okay? And both C and R can be implemented only using logical operations. And somebody's going to say, aha, but you do have an addition here, haha. That cannot be done using just logic gates. Yes?
Just use the lesson that we just established to replace the addition.
But then you have a recursive problem. So the question now is, can I replace this actual addition using OR? So you look at OR and you look at addition. There's only one time that they do not agree when digits are binary, right? Because 0 or 0 is 0, but 0 plus 0 is also 0. Cool. 1 plus 0 is a 1. 1 or 0 is also a 1. 0 and 0 plus 1 is a 1. 0 or 1 is also a 1. The only time they disagree is 1 or 1 is a 1, but 1 plus 1 is a 2. So the question is, can it happen? Can we have carries in both cases? The answer is no, you cannot have carry in both cases. If x0 plus y0 has a carry, q0 plus k0 cannot have a carry, and vice versa. So that means we can now take this plus away and say, haha, we can just use an OR. In other words, the takeaway so far is we can, in fact, use only logical operations, Boolean operations, to perform what we otherwise know as arithmetic operations. Now that is a big jump, okay? Yes?
Is that K0 saying K0 equals not 0?
So K0 is usually assumed 0. Yeah, that's what it's representing. Yep. So what I need you guys to do is to read the notes at least up to where we are, and if you can read ahead, that's even better, okay? Because what is coming through here, okay? They seem to be pretty easy, okay? This seems pretty easy, okay? I mean, we have done this already, okay? Just using different notations, and we have done this already, okay? So you would think we are almost done. But section 6, which is titled, but wait, there's more? I should have said, but there's way more, okay? Because this is where things gets a little bit, let's just say, interesting, okay? So on Thursday, We're going to pick it up from here, and then I will explain why this is actually important. Okay, this is called carry look ahead mechanism. Okay, so we'll deal with this. So I'll see you guys over at the lab, and remember, you have to start a lab, within the section of time, from here to 10 o'clock, because I'm using that to take roll. So I'm going to stop the recorder for now, and I'll see you at the